This is an introduction to exercise 17D on confidence intervals for the population proportion. There are quite a lot of things that we need to cover for this one, so I'll try to keep it as brief as possible, but this is the last exercise. In practice, we analyze samples to further understanding of a population from which they are drawn. We know that what is in a sample, and using that we can infer something about the population. Okay, so using the information about the sample, we can try to use that to try and see whether it would be an accurate estimation of the larger population. A point estimate of P is a single valued estimation of the population proportion P from the sample proportion. So it's a single value, that's it. A point estimate, just like the name implies. Whereas a confidence interval, an interval estimate for the population proportion P. Right, so we're saying, instead of just saying a single estimate, we're saying it could be between here and here. And oftentimes, a confidence interval, it literally is just you pick some numbers you think would be an accurate estimation. But what we're going to be doing is finding a 95%, and this is a specific one, a 95% confidence interval. And it's given by this formula here. Okay? And just to be clear, it is not saying that 95% of our data is within here. That is not what we're saying. In fact, what we're saying is that we have a 95% chance that the actual value is going to be between these 2 points. P represents the population proportion. It's unknown for us. The P hat is a value of the sample proportion, and N is the size of the sample from which P hat is calculated. Let's jump into an example. But before we do that, I do want to remind you that this is still considering that NP and N multiplied by 1 minus P are still greater than 5 for a large sample. We're still assuming that. Okay. Oh, it's having a hard time. Let me know if that cuts out, by the way. Alright, so find an approximate 95% confidence interval for the proportion P of primary school children in Australia who regularly use social media. If we select a random sample of 20 children and find the sample proportion P hat to be 0.7. So again, I'm going to find my values. P hat, I'm going to say is 0.7, and my N is going to equal to 20 as my sample size. I'm going to use my formula. I'm going to start by that's not what I wanted to happen. There we go. I'm going to start by looking for this section of my formula. Right? Because that's the same on both sides, isn't it? So using that section, I know that the square root of P hat multiplied by 1 minus P hat over N, and you'll recognize it looks quite similar to our standard deviation, equals, and I'm going to substitute my values into 0.7 multiplied by the probability of failure, divided by my sample size, which is 20, which equals to 0.1025 when you put it in your calculator. I guess I should put CAS in there. There we go. Alright. Now, using my 95% confidence interval formula, for the 95% confidence interval, apologies for the horrible handwriting, we can say that it's between 0.7, because my formula starts off with the probability minus 1.96 multiplied by the value that we just calculated, so 0.1025, comma, and then it's the probability adding on, that's not 0.5, sorry, it's 0.7, adding on the 1.96 multiplied again by that square root value we found earlier. Putting that into a calculator yields a 0.499 to 0.901. Do note, however, also that if we put in n times p and n times 1 minus p, we do get a value greater than 5. Just note that as well. If I was to interpret this, I would say that there is a 95% confidence in the idea that the estimation, or the actual proportion, actual sample proportion, will be between 0.499, and 0.901. It's quite a large range, isn't it? Now, before we move on, what is one way, and you might want to refer to the formula, what is one way that we can make this estimation, more accurate? How can we minimize or make more narrow that 95% interval? If I told you to do an experiment studying, let's say, for example, the amount of people in Bologna that use social media, and you said, we'll use a classroom as a sample size, how could you get an estimation that's more accurate, more reflective of the whole Bologna College cohort? Yeah. Perfect. If you increase the sample size with the same 95% confidence interval, your values will get closer together. Move on to page 33. Interpreting that interval. Remember that the probability of 0.499 to 0.901, where p is in the middle, of course, does not equal to 0.95. That is not what this calculates. Instead, we're saying that approximately 95% of such individuals, or intervals, here we go. Approximately 95% of such intervals contain the population proportion of P. On the right-hand side, you can see the blue value where we've calculated the confidence interval. Okay? Now, the confidence interval on the right-hand side obtained when 20 different samples were drawn from the same population. The round dots indicate the sample estimate in each case. All of the intervals except one, which I believe is, where is it gone? Am I going blind? Here we go. All of them except one are within or capture that value of P, or that population value, proportion. All of them except one in a sample of 20, which gives us a 95% interval. 95% confidence, Okay, so again, it's not that this probability, using this formula, gives us probability is 95% between those, but rather that we have 95% expectation that the value is there between that in that interval. Example 42. A survey found that 237 of 500 undergraduate university students intended to take a postgraduate course in the future find a 95% confidence interval for the proportion of undergraduate students intending to take a postgraduate course. A lot of words. But basically what we're focusing on is 237 out of 500. And we say a 95% confidence interval is what we're focusing on. So what we can do is go into our calculator again. We're going to open up our statistics. So menu, statistics. I'm going to clear all just for my sake. Here we go. And we're going to go to calculate and then interval, and then 1 prop z. So you should have statistics, calc at the top, select interval, and then you go to 1 prop z. Any questions so far? Okay. You hit next. Your confidence level, of course, or your C level, is of course your confidence level. If you're not sure, you can always press the help button and it will tell you what those values all mean. But C level, we put in 0.95. Our X value is the data, or in this case, as you can see in the parameter, it says the number of successes. So that's going to be 237. Out of n, which is a sample size, so that's the total 500 students that we're looking at. So what you should have written down is 0.95, 237, and 500. You hit OK or Next, and it will give you a bunch of information. Obviously, the sample size hasn't changed. It'll give you the p hat, but the focus right now is on the lower and upper bound. Those are your interval restrictions. So you should have 0.43, let's round it 2 decimal places, 0.43, and you should also have 0.52 as well. So there is a 95% expectation that approximately 95% of such intervals, so this interval contains the population proportion P. Let's move on. Precisions and margins of error. So, in this case, is this another, I think I put another example. Sorry, I should have example at the top of it, but this is another example. In this case, the precision of an estimate is based on the idea that the standard deviation needs to be as small as possible, right? We want our value to be as accurate to the genuine value as possible. In this case, it's the exact same question as above, as question 41, but in this case, the only difference is that instead of a sample size of 20, we're going with a sample size of 200. I'm not going to bore you with the steps because you guys have already done this, but I'll write down the same as well. If you find your square root of p hat multiplied by 1 minus p hat over n, over 200, sorry, in this, we'll leave it as n now, you end up with 0.324, and your range, or your interval, is 0.636 to 0.747664. There we go. So, it is still 95% confidence interval. We are still using the same proportion. However, we are what looks to be about a 0.13 difference, whereas if we scroll back all the way here, that looks to be about a 0.4 difference. Yeah? So if we drastically increase the sample size, we'll get a drastically more accurate or a narrower interval for our 95% confidence. Any questions? Okay. So, our precision is directly linked to our margin of error. So, in order for something to be very precise, we need to have a very low margin of error. It's inversely proportional. So, margin of error, M, is defined as the distance between the sample estimate and the endpoints of a confidence interval. Now, I need you guys to either highlight or circle, whatever it is. Note that this is specifically for a 95% confidence interval. And the same thing applies for that second formula we get by rearranging for n. So m equals to 1.96 and then multiplied by that square root that we're familiar with. It's the same as before, but it's our mean, or our proportion value, multiplied by this value here. So that's our margin error. Rearranging for n, so sample size, gives us this formula, which is still referring to the 95% confidence interval. In general, we use this formula here. Well, we don't, so let's say it's not a 95% interval. But I'll refer to that in a moment, okay? But note that the margin of error is a function of sample size n, and as we mentioned earlier, one way to make that interval narrower, or increase the estimation precision, is to increase the sample size. I'm going to jump to example 43. In this case, determine the sample size required to achieve a 2% margin of error and an approximate 95% confidence interval for the proportion P of primary school children in Australia who use social media. Similar question, except instead of me telling you to find that 95% confidence interval, I'm going to tell you to find what the sample size n needs to be in order for our margin of error to be 2%. Using the formula from above, the one right here, I know that we can say that m equals to 0.02, which equals to 1.1, so that should be a 9, sorry, 1.96 multiplied by the square root of 0.7 multiplied 0.3 divided by n, because we don't know what n is. If you would like, you're welcome to skip that rearranging step and solving step and jump straight into using this formula, which is just the rearranging of that margin of error formula to get our sample size. So rearranging that gives us n equals 1.96 over 0.02 squared multiplied by p, which we know is 0.7, multiplied by 0.3. And you get n equals, well, let's say approximately, because we are rounding it, approximately 2016.84, which you round up to 2017. To answer this question, essentially what I'm saying is that to achieve a 2% margin of error, we need a sample size of at least, or of, let's say, 2017. So n equals 2017. Any questions? One more example and then we're done. Example 44, calculate and compare. Now, what happens if we have to try and calculate it when the value is not a 95% interval, but instead, 95% interval, sorry, but perhaps a 90% interval? So in this case, oh, actually, before we even do that, what can you expect about the interval? If we only need a 90% interval, confidence interval, is that going to be more broad or narrower? If we compare to a 95% for a 90% confidence interval. So let's say a 95% interval is between here and here. I'm saying that I'm saying approximately 95% of the data should be between there and there. If I only need, that's a very loud set of lines. If I only need 90%, it makes sense that I can make that interval narrower because I only need 90% confidence. But let's prove that mathematically. So let's look at the 95% interval. Using the same method, I'm not going to bore you with it. Using the same method, we end up with 0.636, 0.764. Okay, that's using the same method as before. To find 90%, we have to use this idea above, where probability of negative k to z to k, I should say less than, is equal to c over 100. So, the probability of negative k being less than z, being less than k, is 0.9, 90% of course. And we can use the inverse norm CDF, where we have the parameters left, 0.05, 1, and 0. I'm assuming you guys remember this from your previous chapter. We can put that in a calculator. Let me exit this, go to main, interactive distribution. We're going to go inverse norm CDF. We're going left, and again, you could go right, 0.95, that's up to you. Probability is 0.05. Standard deviation once, mean is 0. And we end up with negative 1.65. 5. There we go. And then we use the same formula as above with our standard, our general. I should scroll up so you guys can see. There we go. With our general application, right? So we say the 90% interval is where we have 0.7, because that probability has stayed the same. And we subtract 1.645 multiplied by our square root of 0.7 times 0.3 over 200. That has stayed the same for our 90% interval. To 0.7 plus 1.645 square root of 0.7 times 0.3 over 200. And we end up with an interval of 0.647, 0.753. Comparing these two, which one is narrower? The 90% one. If we have a 99% confidence interval, are we expecting that to be wider or narrower? Wider. To be more confident in your answer, you have to cast a larger net. So, again, you can do the same principle. I'm going to write it up the top here because I'm not going to bore you with the details. 99% gives us 0.616 to 0.784. Again, an even larger interval. This is the key takeaway from this. Being more confident that the confidence interval captures the true value of the population means that a wider interval is required. In order to be more confident, you need to cast a wider net. Okay.